Hello, good day. Welcome to our video lecture series on separation processes. In this video, we'll be talking about binary distillation, more specifically developing material balances to utilize in the Cape-Tail method. Now, the first step is to understand how to develop a material balance. It stems from this equation that you can see here. Accumulation is equal to input minus output plus generation minus consumption. Once you understand this basic equation that is used for any material balance, for any of your specific needs, you can change it and manipulate it to suit your specific needs. So therefore, we'll be constructing different material balance for a distillation column, which is shown here, and we assume that this distillation column is operating at steady state or at a constant volume, so therefore our accumulation term would be equal to 0. We assume that there isn't any reaction taking place in this distillation column, so both the generation term and the consumption term goes to 0, which leaves 0 is equal to input minus output. And you can write that at the side. Input is equal to output. And this basic equation would be utilized throughout this video series and to solve the different material balance. So what we must do first is to set our system boundary. For this first material balance would include everything within the distillation column, including the condenser and the reboiler. Therefore, this blue line represents our system boundary. Now, utilizing our system boundary, we must first identify what type of material balance that we may first write. Our first material balance should always be a total balance. A total balance. Now, this total balance, we utilize the flow rates of each of the streams entering and exiting the column. So, as you can see here, the only flow rate that is entering is the feed, which has a flow rate of F moles per hour, or kilomoles per hour, or kilograms per hour. So that is the only flow rate that is entering, and the flow rates that are leaving are the distillate, which is D, plus the bottoms product or the waste, which is W. So this is your first material balance. The second material balance that you may want to write is the component balance. Now, given that this is a binary distillation system, you expect there would only be 2 components, so therefore you can write the balance for either component. Now, in this case, we have a flow rate F, a component, the most volatile component, composition of ZF. We have a distillate D, the composition of the most volatile component in the distillate is ZD, the flow rate W, and the composition of the most volatile component in the waste or the bottoms is XW. Now, the differences between X, you'll see X, you'll see Z, and you will also see Y is basically the state at which the mixture is in. Z represents that it can either be liquid, it can be gas, or it can be both liquid and gas. That is why we utilize Z. X is represent for the mole fraction of solely in the liquid phase, and Y is represents the mole fraction solely in the vapor phase. So if we commence and to write the component balance for the more volatile component in this system, as I said before, we start off input is equal to output. The only input material coming in is the feed. So our component balance for the feed, for the most volatile component that is, would be F, which would have units kilograms per hour, kilograms per second, kilograms per minute, kilomoles per hour, kilomoles per minute, kilomoles per second, and the mole fraction of the most volatile component. In this case, it is ZF. Again, for the binary system, you will have two components within your feed, so therefore you will basically have a component ZF1 and ZF2. However, as I said, I'll be utilizing the mole fractions of the most volatile component. So this is the component balance for the most volatile component. So we have the feed that is coming in. What is coming out now, we utilize our distillate. As you can see, whatever cuts the system boundary, we utilize. So therefore, the distillate cuts the system boundary. That is the material leaving the system, which will be D, capital D for the flow rates, multiplied by the mole fraction of the most volatile component leaving, which is ZD, plus, again, the bottoms product or the waste product is leaving the system, and that has a flow rate of W, and you multiply by the mole fraction of the most volatile component in the bottoms product, which is XW. Now this is your second balance that you can utilize to solve for possibly the unknowns within the system.